A star is vanishing right before our eyes, and no one knows why. This is not science fiction. It is a real astronomical mystery playing out in the depths of our galaxy, one that has the world's top scientists completely stumped. By the end of this journey, you will understand the full, astonishing story behind a star whose bizarre behavior defies every textbook explanation. We will explore vanishing acts of impossible scale, debate the shadow of alien megastructures, and follow a global hunt for answers. How do you solve a cosmic crime when the evidence makes no sense? The star at the heart of this cosmic detective story is known as KIC 8462852, but most simply call it Tabby's star. It sits in the constellation Cygnus, the Swan, roughly 1,400 light-years away from Earth. To understand why this particular star is so baffling, you first need to know how a star is supposed to behave. Under normal circumstances, a star like our own Sun is a model of consistency. Its brightness is a steady, unwavering beacon, a predictable furnace of nuclear fusion. When we see a star dim from our vantage point, it is almost always for a clear and simple reason. A planet, for example, will pass in front of it, causing a brief, symmetrical, and perfectly repeatable dip in its light. It is like watching someone walk in front of a street lamp, a clean, predictable shadow. This is the rhythm of the cosmos, a clockwork universe we have learned to read. But Tabby's star does not follow the rules. Its light does not dip in those neat, predictable patterns. Instead, it fades by staggering amounts, sometimes by more than 20%, in chaotic, asymmetrical plunges that last for days or even weeks. Then it might stay dim for years before slowly, unevenly recovering. This is not a planet. It is as if the street lamp itself is flickering and dying, controlled by a switch no one can find. The central question became terrifyingly simple. What object or what process could possibly block such an immense amount of starlight? The first clue arrived not from a seasoned astronomer in a mountaintop observatory, but from the keen eyes of ordinary people staring at data on their home computers. This was the work of the Planet Hunters, a global team of citizen scientists who volunteered to sift through the mountains of information sent back by NASA's Kepler Space Telescope. Kepler's mission was simple yet profound: to stare at one patch of sky, watching over 150,000 stars for the telltale, repetitive dimming caused by orbiting planets. It was looking for cosmic clockwork, the gentle, predictable rhythm of shadows. But in the data for one unassuming star, the volunteers found something that made no rhythm at all. They flagged it as curious, then bizarre, and finally impossible. This was the first glimpse of what would become known as the Great Dimming. The data painted a picture that shattered all expectations. A typical planet transit, like one from a Jupiter-sized world, might cause its star to dim by about 1%. It is a subtle, almost elegant blink. What Kepler recorded from Tabby's star was not a blink. It was a blackout. The star's light plummeted by up to 22%, a drop so severe it was as if a quarter of the star's very face had been suddenly erased. And it did not happen just once. Over Kepler's 4-year mission, the star dipped repeatedly, but with no discernible pattern. The dimmings were deep, irregular, and lasted for wildly different lengths of time, sometimes days, sometimes over a week. The shape of the light curve was all wrong, too. A planet creates a symmetrical U-shaped dip as it neatly crosses the star's disk. The dips from Tabby's star were jagged and lopsided, like a broken silhouette scraping across the light. This was not a clean shadow from a spherical object. Whatever was causing this was colossal, blotting out an area far larger than any conceivable planet, and it was shaped in some profoundly strange, asymmetric way. The data was a scream of wrongness in a universe of order, a single line on a graph that asked a question science was not prepared to answer. That single line on a graph launched a frantic race to find a culprit. The first step in any good investigation is to rule out the obvious, and for a star behaving badly, the list of usual suspects is surprisingly short. Astronomers began with the simplest, most natural explanations, the kind of cosmic events we have seen before. Their first thought was a colossal swarm of comets. Imagine not one or two, but thousands of icy bodies, each trailing immense clouds of gas and dust on a chaotic orbit around the star. As this fractured army passed in front of Tabby's star, the thinking went it could create those deep, irregular dips. The dust from their tails would block the light in a messy, unpredictable way. For a moment, it seemed like a plausible answer. We have seen cometary swarms around other stars. But the scale was all wrong. To dim a star by 22%, you would need a number of comets so vast it beggars belief, a swarm larger than any ever observed in our own solar system by orders of magnitude. And such a swarm would have to be on a precise, repeating orbit to cause the multiple dips seen over years. The universe is chaotic, and maintaining that kind of orderly chaos for a swarm of that size seemed, frankly, impossible. It was like trying to explain a city-wide blackout by blaming a few thousand flickering candles. The next suspect was even more dramatic, a planetary catastrophe. What if we were witnessing the aftermath of a titanic collision, the destruction of an entire world? The impact would vaporize rock and metal, hurling an enormous, opaque cloud of debris into orbit around the star. This cloud, slowly drifting and changing shape, could certainly cause the deep, irregular dimmings. It is a theory with a cinematic scale, but science demands evidence, not just spectacle. A collision of that magnitude would release an enormous amount of energy, heating the debris to incredible temperatures. That heat would glow brightly in infrared light, the same way warm asphalt radiates heat after a sunny day. Our most powerful telescopes, like NASA's Spitzer Space Telescope, turned their infrared eyes toward Tabby's star. They searched for that telltale warm glow, the signature of a cosmic crime scene. They found nothing. The star's infrared output was perfectly normal. There was no hot dust cloud, no lingering heat from a shattered planet. The evidence for a cataclysm simply was not there. So the detectives turned to a more mundane possibility, cold dust, not from a collision, but from a natural, thick ring of cosmic debris, like Saturn's rings but on a stellar scale. Cold dust does not glow in infrared, so its absence would explain the Spitzer findings. It could, in theory, clump and drift, creating those lopsided shadows. Yet again, the details betrayed the theory. Dust, by its very nature, scatters starlight. It does not just block it, it redirects it, changing the color of the light that gets through. Think of a sunset where dust in our atmosphere scatters blue light, leaving the red and orange to paint the sky. If a cloud of dust were causing Tabby's star to dim, astronomers expected to see it dim more in blue light than in red light. But the observations showed the opposite, or showed no color change at all. The dimming was achromatic, meaning it blocked all colors of light equally. That is the signature of something solid and opaque, like a planet, not something fluffy and diffuse like a dust cloud. One by one, the comfortable explanations from the astrophysics textbook were crossed off the list. A comet swarm was too improbable. A planetary collision left no heat signature. A dust cloud did not scatter light the right way. Each door was closing, leaving scientists in a room with fewer and fewer exits. The conventional wisdom had run out, and the true strangeness of Tabby's star was only beginning to come into focus. With every natural explanation failing, the investigation took a sharp turn into the realm of science fiction. If no known cosmic phenomenon could explain the data, then perhaps the answer was not natural at all. Perhaps it was artificial. This was the moment the alien megastructure hypothesis was born, a theory so audacious it would transform Tabby's star from an astronomical oddity into a global headline. The idea was championed by astronomer Jason Wright from Penn State University. He looked at the same baffling evidence: the colossal, irregular dimmings, the achromatic light, the lack of infrared heat, and asked a revolutionary question. What if we are not looking at a natural object, but at a piece of technology? Specifically, he proposed the possibility of a Dyson sphere, or more accurately, a Dyson swarm. The concept comes from physicist Freeman Dyson, who speculated that a civilization far more advanced than our own would eventually need to capture the entire energy output of its star to power its growth. They would not build a single solid shell, an impossible engineering feat, but rather a vast swarm of energy collecting satellites or habitats orbiting their sun. This swarm would be colossal, blocking a significant fraction of the star's light, and its structure would be uneven and incomplete, creating those jagged, asymmetric dips in brightness as it rotated. Think of it not as a solid ball, but as a thick, lopsided ring of countless solar panels drifting in a loose formation around their power source. For the first time, the bizarre data had a framework that actually fit. A megastructure swarm could be large enough to block 22% of the starlight. Its rigid, solid components would dim all colors of light equally, matching the achromatic signature. And because it was not a cloud of hot dust, it would not glow in infrared, explaining the silent readings from Spitzer. It was, in a purely theoretical sense, a perfect suspect. Wright was careful to frame it not as a claim of discovery, but as the last hypothesis standing after all others had fallen. He argued that when you exhaust the natural explanations, the artificial one deserves a place at the table, if only to be rigorously tested. But the moment the words alien megastructure entered the public discourse, the story exploded. The idea was a cultural lightning rod, tapping directly into our deepest wonder about whether we are alone in the universe. It was no longer just a story for astronomers, it was a mystery for all of humanity. Tabby's star became a sensation, its name splashed across news sites and social media. Suddenly, everyone was asking the same thrilling, terrifying question. Were we, for the very first time, looking at the handiwork of another civilization? The hunt for answers was no longer just about astrophysics. It had become a search for neighbors. The alien megastructure idea was a thrilling possibility, but in the halls of science, thrill is not proof. For every headline shouting about Dyson spheres, there were teams of researchers urging a deep, collective breath. The core principle guiding them was one articulated by the late astronomer Carl Sagan: extraordinary claims require extraordinary evidence. And a claim of intelligent alien life engineering structures around a star is about as extraordinary as it gets. The scientific pushback was not about dismissing imagination, but about defending the rigorous, often painstaking process of discovery. They argued that before we rewrite the textbooks with tales of alien engineers, we must be absolutely certain we have exhausted every single natural explanation, no matter how unlikely it might seem. The history of astronomy is littered with mysteries initially attributed to intelligence, from the canals of Mars to the pulsating signals of pulsars, which were briefly nicknamed LGM for little green men. In every case, a deeper look revealed a natural, if surprising, cosmic phenomenon. The odds, therefore, favored Tabby's star being another chapter in that story, not the first sentence of a completely new one. This skepticism created a vital tension. On one side was the captivating, paradigm-shattering idea of a technological signature. On the other was the sobering weight of probability. As astrophysicist Ethan Siegel pointed out, the universe is vast and filled with processes we do not yet fully understand. Invoking aliens to explain a gap in our knowledge is what philosophers call a God of the Gaps argument, just dressed in technological clothing. It is a shortcut that can halt real investigation. The media frenzy, while exciting, often amplified this shortcut. News outlets found the alien angle irresistible, sometimes presenting it as a leading theory rather than a last resort hypothesis. This created a public perception that scientists were on the verge of confirming alien builders, when in reality, most were deeply skeptical and hard at work looking for a cosmic culprit that did not require a consciousness behind it. This gap between public excitement and scientific caution became a story in itself. Prominent voices in the field were clear and measured. Astronomer Jill Tarter, a legendary figure in the search for extraterrestrial intelligence, reminded everyone that the search is a marathon, not a sprint. She emphasized that the true strength of the scientific method is its ability to self-correct, to follow the evidence wherever it leads, even if that leads away from the most exciting answer. The goal was not to prove the alien hypothesis, but to solve the mystery, period. This careful, deliberate approach is what separates science from speculation. It is why, instead of declaring a discovery, astronomers did what they always do. They pointed more telescopes at the star, gathering every possible wavelength of light, searching for any clue, any anomaly that could point toward a definitive answer. The alien hypothesis, for all its allure, was not the end of the story. It was a catalyst that ignited the most intense observational campaign ever directed at a single, seemingly ordinary star. The real work was just beginning, and it would require patience, precision, and a willingness to be surprised by the universe in ways no one had predicted. The alien megastructure hypothesis forced astronomers to look at Tabby's star with entirely new eyes, but it also demanded they gather evidence with unprecedented precision. The world's most powerful telescopes, from the giant Keck Observatory in Hawaii to the Los Cumbres Observatory network spanning the globe, all turned their gaze toward that one point of light in Cygnus. They were not just watching for the next big dip, they were dissecting the star's light across every color of the rainbow, searching for the faintest whisper of a clue. What they found next added a whole new dimension to the mystery, one that was slower, deeper, and even more perplexing than the sudden blackouts. Beyond the erratic dips, Tabby's star was itself fading away. This was not a quick flicker. It was a long, slow, relentless decline in brightness measured over years. While the Kepler mission had captured the star's dramatic plunges, other telescopes were quietly recording this more gradual change. But to truly understand the scale of what was happening, scientists had to look back in time, long before Kepler was even launched. They turned to a unique historical archive, over a century's worth of astronomical photographic plates. These glass plates, stored in observatory vaults, contain a literal snapshot of the night sky from generations past. A team led by astronomer Bradley Schieffer dove into this treasure trove, carefully measuring the brightness of Tabby's star on plates dating back to the 1890s. The result was astonishing. The historical record showed that, overall, Tabby's star had been dimming for at least 100 years. In that time, it had faded by a staggering amount. Roughly 20% of its total light output had simply vanished. Think of it this way: if the short-term dips were like someone randomly turning a dimmer switch down for a few days, this long-term trend was like that same switch being slowly, steadily cranked downward over an entire human lifetime. This changed everything. The mystery was no longer just about what was passing in front of the star. It was now about something happening to the star itself, or to an immense structure surrounding it. A century-long dimming is catastrophically difficult to explain. Natural cosmic events tend to be either brief and violent or operate on timescales of millions of years. A 100-year trend is a geological blink of an eye in stellar terms. What process could envelop a star and make it significantly dimmer over a mere century? A swarm of comets was utterly ruled out. No comet swarm could persist in a dense, light-blocking formation for that long. A dust cloud from a planetary collision would have either dispersed or been absorbed by the star by now. Even the alien megastructure idea had to evolve under this new pressure. A Dyson swarm under construction could, in theory, cause a steady dimming as more and more collectors are put in place. But building something that blocks 20% of a star's light in just 100 years is an engineering project of almost incomprehensible speed and scale, even for a super-advanced civilization. The long-term dimming pointed toward something immense and semi-permanent. It suggested a cloud of material, whether natural or artificial, that was not just passing by but was in a stable orbit around the star, consistently blocking a portion of its light from our view. But again, the achromatic nature of the dimming, the fact that it blocked all colors of light equally, argued against ordinary dust. This left scientists grappling with a paradox. They needed something with the opacity of solid objects, but spread across a volume of space large enough to shroud a star for a century. Every proposed solution seemed to create two new problems. The slow fade was a deeper, more fundamental puzzle than the sharp dips, a bass note of wrongness underlying the erratic melody of the star's behavior. It meant the star's true nature was hidden behind a veil, and we had only just begun to sense its outline. The century-long fade forced astronomers to consider a radical possibility. What if the culprit was not in front of the star, but was the star itself? This shifted the entire investigation from a search for orbiting objects to an examination of stellar physiology. Could internal processes, some strange stellar heartbeat or fever, cause a star to dim so profoundly? The first suspect was starspots. Our own sun has them, cooler, darker regions on its surface caused by intense magnetic activity. When a large group of sunspots rotates across our view, the sun's total brightness dips by a tiny fraction of a percent. Could Tabby's star be covered in monstrous, continent-sized starspots enough to block 20% of its light? The math immediately presented a problem. To achieve that level of dimming, nearly a quarter of the star's entire surface would need to be covered in these cold, dark patches. We have never observed a star with such extreme spot coverage. More importantly, as a star rotates, spots come in and out of view, causing a rhythmic, predictable dimming that repeats every rotation period. The dips from Tabby's star are neither rhythmic nor predictable. They are chaotic and can last for weeks, far longer than the typical rotation of such a star. Star spots, while a good thought, simply could not scale up to explain the evidence. Next, scientists looked to stellar pulsations. Some stars, known as variable stars, naturally breathe in and out, growing brighter and dimmer in regular cycles. But Tabby's star is classified as an F-type main sequence star, a category that includes stars slightly hotter and more massive than our Sun. These stars are known for their stability. They are not the pulsating, variable types. Their nuclear furnaces burn steadily, and their light output is famously consistent. Asking an F-type star to perform the erratic dimming act of Tabby's star is like asking a metronome to suddenly break into a jazz solo. It goes against its fundamental nature. The observed behavior is 1,000 times more extreme than any known pulsation for a star of its class. Furthermore, pulsations would cause the star's temperature and spectrum to change in specific, detectable ways. Detailed spectroscopic analysis of Tabby's star revealed no such changes. Its light, when not being blocked, was perfectly normal for its type. This was a critical finding. It meant the star itself was not sick. It was not undergoing some internal convulsion or magnetic tantrum. The engine at its core was running smoothly. The problem, therefore, had to be external. But if it was external, it had to be something that did not scatter light like dust, did not glow in infrared like hot debris, and could persist for a century. The investigation had cornered itself. The star was innocent of the crime, but the evidence of the crime was etched into its light. This left scientists staring at a paradox with only one path forward: to catch the culprit in the act, to witness a major dimming event in real time with every instrument at their disposal. The world was watching, waiting for the star to perform its most mysterious trick yet. The star seemed to guard its secret with a wall of contradictory evidence, but science has a way of patiently chipping away at even the most stubborn mysteries. The real breakthrough came not from a single dramatic moment, but from a careful, coordinated effort to watch Tabby's star with a wider set of eyes. Astronomers knew they needed to catch the star in the act of dimming, and to observe that dimming across the entire spectrum of light, from the energetic blue to the long, warm waves of infrared. This was a stakeout on a cosmic scale. They got their chance in 2017. Over several months, the star began one of its long, deep fading events, dimming by nearly 10%. This time, the world was ready. Telescopes around the globe and in space, including NASA's Spitzer Space Telescope, which sees in infrared, and the Swift Observatory, which sees in ultraviolet and visible light, all turned to watch in unison. The data they collected would finally tip the scales decisively in one direction. What they found was a subtle but critical clue hidden in the colors of the dimming light. When the star faded, it did not fade evenly across all colors. The dimming was much more pronounced in blue light than it was in the infrared. This difference is a classic fingerprint, a smoking gun for one specific culprit: dust. To understand why, think of a hazy day on Earth. The sky is not black, it is a diffuse, milky blue. That is because the tiny dust particles and molecules in our atmosphere scatter shorter wavelength blue light much more effectively than they scatter longer wavelength red light. The blue light gets bounced around in all directions, while the red light travels more directly to your eyes. This is why sunsets appear red. The blue light has been scattered away on the long path through the atmosphere at the horizon. The same physics applies in space. A cloud made of very fine, microscopic dust grains will scatter and block blue light more than red or infrared light. If the object blocking Tabby's star were a solid, opaque structure, like a planet or a piece of an alien megastructure, it would create a clean shadow, blocking all wavelengths of light equally. That achromatic signature was what had made the alien hypothesis so compelling in the first place. But this new multi-wavelength observation revealed the truth. The dimming was chromatic, it had a color to it. The fact that blue light was being preferentially filtered out meant the blocking material could not be solid and monolithic. It had to be made up of countless tiny particles, each smaller than a grain of talcum powder, floating in a vast, diffuse cloud. This was the evidence that finally broke the case wide open. The infrared data from Spitzer was particularly damning for the megastructure idea. If a solid swarm of satellites or panels were causing the dimming, the infrared light should have dropped in lockstep with the blue light. Instead, the infrared dimming was measurably less. The universe was telling us in the clear language of physics that we were looking at dust, not the hot dust of a collision, which Spitzer would have seen glowing brightly, but cold dust, drifting in a complex, uneven swarm around the star. This did not instantly solve the entire mystery, far from it. We still do not know the origin of that dust or why it behaves in such a bizarre, clumpy fashion. But it did something profound. It pulled the investigation firmly back into the realm of natural astrophysics. The most extraordinary claim, the signature of intelligence, had finally met the extraordinary evidence required to support it, and it had failed the test. The ghost of the Dyson sphere began to fade, not with a bang, but with the quiet, definitive whisper of scattered blue light. Dust may be the culprit, but this is no ordinary dust cloud. The evidence demands something far more chaotic. Those deep, lopsided dips in the star's light tell us the dust cannot be spread out in a smooth, even ring like Saturn's. Instead, it must be concentrated in dense, irregular clumps, swirling in a messy, asymmetric swarm around the star. Imagine a construction site orbiting a sun, with piles of debris of all shapes and sizes drifting in and out of formation, casting jagged, unpredictable shadows. This is the kind of chaotic environment we are trying to picture. So where could such a messy swarm of dust come from? One leading idea points to a cosmic catastrophe. Picture a catastrophic collision between two planets, or perhaps a planet and a massive moon in the star's system. The impact would not be a clean event. It would shatter worlds, vaporizing rock and metal and hurling an unimaginable amount of debris into orbit. This debris would not form a neat ring instantly. Instead, it would be a chaotic, churning cloud of fragments, from mountain-sized boulders down to fine powder, all on slightly different orbits. Over time, gravity and collisions would cause this cloud to clump and spread unevenly, creating exactly the kind of lumpy, opaque swarms that could produce those strange light curves. Another possibility is a vast, hyperactive asteroid belt, far denser and more violent than our own. In our solar system, asteroids collide, but it is a rare and relatively gentle process. Around Tabby's star, we might be looking at a belt in a state of perpetual chaos, with constant grinding collisions pulverizing asteroids into vast plumes of dust. This would be a factory of debris, continuously replenishing the cloud and keeping it thick and clumpy. The irregular dips could then be explained by the largest collision events or by the chance alignment of the densest dust trails as they orbit. A third, more subtle idea involves a migrating planet. If a giant planet like a Jupiter were slowly moving inward through a system rich with smaller bodies and dust, its immense gravity would act like a cosmic snowplow. It would stir up the material in its path, shattering icy moons and perturbing asteroids, creating a turbulent, dusty wake that trails behind it. This wake could be the asymmetric cloud we see, with the planet itself hidden in the glare of the star. All these scenarios share a common theme: immense, ongoing chaos. This is not a quiet, settled system. It is a dynamic and violent environment, a place where celestial bodies are still crashing together, where orbits are unstable, and where dust is the dominant feature. The mystery of Tabby's star has evolved from a search for alien engineers to a study of planetary system adolescence gone terribly wrong. We are likely witnessing the messy aftermath of a dramatic event, or perhaps an ongoing process of destruction, on a scale our own solar system has not seen for billions of years. The story of this star grows even stranger with another piece of the puzzle. While most of the focus has been on its dramatic dimming, careful observations have also captured something just as baffling. The star sometimes spikes in brightness. These are not gentle increases, but sudden, unexpected flares where the star's light intensifies for brief periods. Think of a flickering light bulb that not only dims erratically, but also occasionally surges with a blinding flash. This combination of deep blackouts and sharp brightening paints the portrait of an object in a state of extreme, almost violent volatility. It is not just being obscured, it is erupting. This eruptive behavior forces us to consider a new category of explanation altogether. Perhaps we are not looking at the aftermath of a planetary collision, but at the star itself going through a catastrophic developmental phase. Young stars, especially those still forming from collapsing clouds of gas and dust, are known for such tantrums. They can experience immense flares, hundreds of times more powerful than anything our sun produces, and they are often shrouded in thick, clumpy disks of debris, the very material from which planets are born. In these stellar nurseries, brightness can vary wildly as hotspots flare on the surface and as clumps of dust in the disk randomly block the light. Could Tabby's star be a youthful sun, a cosmic teenager in the throes of a turbulent adolescence? The problem is its age. Based on its temperature, size, and composition, it appears to be a mature, main-sequence star like our sun, not a newborn. But what if our classification is wrong? Could it belong to a rare, poorly understood class of stars that maintain this hyperactive, dusty volatility for much longer? Another, more dramatic possibility is that we are witnessing a star in a brief, catastrophic transition. Some stars go through phases of intense mass loss, literally shedding their own outer layers into space in great, dusty eruptions. This material could form an irregular, opaque shroud around the star, causing the long-term dimming, while the physical process of the eruption, the violent ejection of superheated plasma, could cause the sudden brightening events. We would be watching a star literally coming apart, unraveling itself over a century rather than an eon. It is a stellar fever dream, a short-lived stage of chaos that few stars ever exhibit and even fewer are caught in the act. The flickering light, then, is not just a shadow play. It is the vital sign of a deeply unstable object, pulsing with eruptions and cloaked in its own expelled material. This reframes the entire mystery. We may not be solving a crime scene from a single past event, but diagnosing the real-time symptoms of a stellar illness. The question is no longer simply what is blocking the light, but what traumatic process is causing the star to both cough up dust and scream with light. But what if the chaos is not coming from within? To solve a mystery of this scale, we must sometimes zoom all the way out to consider forces that operate on the canvas of the galaxy itself. Could the cause of Tabby's star's strangeness lie entirely outside its own system, in the dark spaces between the stars? This line of thinking has led scientists down some of the most exotic and mind-bending paths of all, exploring possibilities that sound like they are pulled from the pages of a theoretical physics textbook. One such idea involves a rogue black hole, not the supermassive monster at the center of our galaxy, but a smaller stellar mass black hole, one wandering alone and invisible through the interstellar void. If such an object, surrounded by its own thick, swirling disk of superheated debris and gas, were to pass directly between us and Tabby's star, it could certainly cause a deep, irregular dimming. The accretion disk around the black hole would be a messy, turbulent thing, casting a complex and shifting shadow. The problem, once again, is probability. The odds of such a perfect, long-duration alignment are astronomically low, and it would not easily explain the century-long fading trend. Another, even more elusive suspect is dark matter. We know this mysterious, invisible substance makes up most of the mass in the universe, but we have no idea what it actually is. Could a dense, drifting cloud of an exotic form of dark matter interact with starlight in a way we do not yet understand? Perhaps, but without a concrete theory for how dark matter blocks light, this remains a speculative placeholder, a confession of our ignorance more than a testable explanation. The most compelling external idea is gravitational lensing. This is a real, observed phenomenon where the gravity of a massive object, like a galaxy or a star, bends and magnifies the light from an object behind it, acting like a cosmic magnifying glass. Could an invisible, massive object, a faint star, a brown dwarf, or even a planet be drifting in the foreground, its gravity subtly warping and distorting our view of Tabby's star? In rare cases, the complex caustics of a lensing event can create brightening and dimming patterns. However, for lensing to produce the observed effects, the alignment would need to be unbelievably precise and stable for over a century, and the predicted light curve signatures do not match the star's erratic behavior well. While these galactic-scale hypotheses are generally considered less likely than the dusty, chaotic system models, they are profoundly important. They showcase the sheer breadth of creative, desperate thinking this single star has ignited across the astrophysics community. When faced with a puzzle that defies all standard solutions, scientists are forced to question their most fundamental assumptions about what is possible. They must venture to the very edges of known physics, considering objects and interactions that are normally relegated to theoretical discussions. Tabby's star has become a catalyst for this kind of radical imagination, a single point of light compelling us to interrogate the darkest, most unknown corners of our galaxy. This global conversation, this collective scratching of heads, was only possible because of a quiet revolution in how we explore the cosmos. The story of Tabby's star is not just about telescopes and theories. It is about people. It is a powerful testament to how modern astronomy has been transformed into a truly democratic, collaborative endeavor, where the sharp eyes of a curious public can guide the focus of the world's most powerful scientific institutions. That first crucial clue, the bizarre, jagged line on the light curve, was not discovered by a PhD in an observatory control room. It was found by volunteers, ordinary people sitting at their home computers who were simply fascinated by the stars. They were part of a program called Planet Hunters, a citizen science project run through the Zooniverse platform. The challenge was monumental. NASA's Kepler Space Telescope had produced a flood of data, light curves for over 150,000 stars. No single team of professional astronomers could possibly scrutinize every single one with a careful, pattern-seeking human eye. Computers are excellent at finding the expected, the repetitive dips of planets. But they can miss the weird, the anomalous, the things that do not fit any pre-programmed template. That is where human intuition becomes irreplaceable. The Planet Hunters volunteers were given a simple, powerful task: look at graphs of starlight and click where you see a dip. They became a global network of pattern detectors, a distributed brain analyzing the cosmos. And among those thousands of volunteers, several individuals looked at the data for one particular star and knew instinctively that something was wrong. They flagged it, discussed it on the project's forum, and brought it to the attention of the professional scientists running the project. Without that human curiosity, that moment of recognition from a non-expert, the star's strangeness might have been lost in the algorithmic noise for years. This is the new face of discovery. The internet has dissolved the walls of the ivory tower, allowing raw data from billion-dollar space missions to flow directly to anyone with a connection and a desire to help. It turns the search for knowledge into a shared adventure. Think of it as a cosmic neighborhood watch with millions of eyes scanning the sky, each person capable of spotting the one flickering porch light on a dark street. This collaboration extends far beyond just identifying curiosities. When Tabby's star began its major dimming event in 2017, it was amateur astronomers around the world with their own backyard telescopes who provided vital continuous coverage. Professionals cannot command telescope time at a moment's notice for unpredictable events, but a global network of dedicated amateurs can fill those gaps, creating a 24-hour watch. Their contributions provided the crucial timeline of the dimming, the detailed play-by-play that allowed the big observatories to know exactly when to point their instruments. This partnership redefines what it means to be an explorer. You no longer need a doctorate or access to a mountaintop. You need curiosity and an internet connection. The mystery of Tabby's star, from its first detection to its ongoing surveillance, is a story written by thousands of authors. It proves that the next great cosmic secret might be uncovered not by a lone genius, but by a retired teacher, a student, or an office worker who simply decided to spend an evening helping science look at the stars. This global network of curiosity became a formal, coordinated assault on the mystery. To truly understand Tabby's star, scientists needed something rare in astronomy: constant, uninterrupted vigilance. Stars do not keep office hours, and a crucial dimming event could begin at any moment from any vantage point on Earth. Catching it required a new kind of observatory, one that never sleeps. That is where the Los Cumbres Observatory Global Telescope Network, or LCO, entered the story. It is not a single telescope on a remote mountaintop. Instead, it is a robotic network of over 20 telescopes, identical in their instruments, spread across the globe at sites in Hawaii, Texas, Chile, South Africa, and Australia. When the sun sets in California, the telescopes in Australia are already turning to the night sky. This creates a seamless 24-hour chain of observation, a planet-sized eye that never blinks. For a star as unpredictable as Tabby's, this capability was revolutionary. The LCO network could watch it continuously, gathering a flawless, unbroken light curve, ready to sound the alarm at the first sign of a dip. Securing this kind of dedicated time, however, is a monumental challenge in modern astronomy. Telescope time is the most precious currency scientists have. Major observatories like Keck or Hubble receive proposals from thousands of researchers, each vying for a few precious hours to study black holes, distant galaxies, or exoplanets. To ask such a facility to point at a single, weird star for night after night, month after month, is an enormous request. It means saying no to other groundbreaking projects. The case for Tabby's star had to be overwhelmingly compelling. It was not just about solving one puzzle. It was about demonstrating that the scientific process itself could mobilize globally to chase down an anomaly, to follow the evidence wherever it led, no matter how strange. The campaign was led by astronomer Tabitha Boyajian, the star's namesake, who became the chief coordinator of this cosmic stakeout. Her team secured time on LCO, but also on other giants like the W.M. Keck Observatory in Hawaii, which could dissect the star's light with breathtaking precision, and even the Hubble Space Telescope, which could look for clues in ultraviolet light invisible from the ground. The goal was multi-wavelength coverage. If the star dimmed, they needed to see not just how much light vanished, but how the dimming changed across the entire spectrum, from ultraviolet to infrared. That color fingerprint would be the key to identifying the culprit. Meanwhile, an army of amateur astronomers stood ready. When professional telescopes are scheduled months in advance, amateurs provide the agile, rapid response. Through organizations like the American Association of Variable Star Observers, hundreds of individuals with telescopes in their backyards or on their rooftops were enlisted. They received alerts and carefully measured the star's brightness night after night, contributing a river of data points that filled in the gaps. This was science at its most collaborative and human. A professor at a world-class university was analyzing data on the same star as a hobbyist in a suburban driveway. They were united by the same question, contributing to the same grand experiment. The logistical challenge was immense, a ballet of schedules, time zones, and weather forecasts. A cloudy night in Chile could mean a critical data point was lost. A technical glitch in Texas could break the chain, but the persistence paid off. When the star began its next significant dimming event, the network was watching. Every dip, every flicker was captured by multiple eyes in multiple colors from multiple points on the globe. This coordinated gaze finally provided the clear, multi-wavelength evidence that pointed decisively toward dust. It was a triumph not of a single genius or a single machine, but of collective, organized wonder. The star did not give up its secrets easily, but humanity was now watching with a patience and persistence to match its mystery. The coordinated global watch on Tabby's star did more than just deepen its mystery. It trained the astronomical community to look for the strange, to expect the unexpected in the steady light of distant suns. And as we began looking with these new, suspicious eyes, a startling realization emerged. Tabby's star might not be a lonely freak of nature. It could be the first known member of an entirely new class of cosmic oddities, a hidden population of flickering, unpredictable stars we had simply never noticed before. Take the star known as Epoch 204278916. Discovered in data from the Kepler telescope's K2 mission, this young, sun-like star displayed a dimming event that makes even Tabby's star seem almost tame. Over the course of just a single day, its light plummeted by a staggering 65%. That is not a shadow, it is an eclipse of impossible depth. The dip was also incredibly sharp and asymmetric, as if a colossal, jagged object with a long, trailing tail ripped across the face of the star, the best explanation. A giant, warped disk of dust and debris, possibly from a shattered protoplanet, orbiting the star and periodically blocking its light. Here was another system in a state of extreme chaos, another case where simple planets could not explain the data. Then there is VVVWIT-07, a giant star observed by a telescope in Chile surveying the crowded bulge of our galaxy. This star faded slowly over a period of 200 days, dimming by an astonishing 80%, nearly vanishing from view before slowly recovering. The shape of its dimming curve was smooth, suggesting a different kind of obscuration, perhaps a dense, dark cloud of dust drifting in the vast space between us and the star. Each of these objects, tabbies, epic VVVs, tells a different story of obscuration, but they all speak the same language of profound, irregular dimming. Astronomers have begun grouping some of these objects under a tentative label, dipper stars. The name comes from the deep, dipping shapes of their light curves. They are not the regular, metronomic variables of old textbooks. They are the erratic, the unpredictable, the deeply shadowed. By finding more of them, we stop asking about one impossible star and start asking about a phenomenon. This shift is critical. In science, a single anomaly can be a fascinating curiosity, but a pattern is a revolution. When you have a class of objects, you can compare them. You can look for common traits. Do they tend to be young or old? Are they often found in dusty regions of space? Do their dimmings share any subtle spectral fingerprints? Finding these connections is how you move from speculation to understanding. The hunt for more dipper stars is now a priority. New space telescopes like TESS, which surveys almost the entire sky, are perfect for this work. They are not just looking for neat planetary transits anymore. Their algorithms are being tweaked to flag the weird, the deep, the irregular. Every new dipper star discovered is another piece of the puzzle. One might be a young star with a warped disk. Another might be an old star experiencing a catastrophic eruption. A third might have a giant planet stirring up a dusty maelstrom. Together, they are teaching us that our galaxy is far more dynamically messy than we ever appreciated. Planetary systems are not always neat and orderly. They can be violent, dusty, and chaotic places for billions of years. The flickering light of these stars is a beacon, illuminating this hidden side of cosmic evolution. We are no longer solving a single mystery. We are mapping the shadowy contours of an entirely new frontier in stellar behavior. Inside the silent hum of supercomputers, a different kind of observation is taking place. Since we cannot travel to Tabby's star and see its chaos up close, scientists are attempting the next best thing: building a digital twin of its entire system inside a machine. This is the world of theoretical modeling, where astrophysicists translate the star's bizarre light curve, that jagged, dipping line, into a set of mathematical rules and physical forces, then hit run to see if their virtual universe can mimic reality. The goal is breathtakingly ambitious: to reconstruct a cosmic car crash using only the pattern of shattered glass left behind. The primary suspect in these simulations is dust, but not as a simple, static cloud. The models must account for a dynamic, churning swarm of trillions of microscopic particles, all under the relentless pull of the star's gravity and the jostling influence of hidden planets. Each particle has a size, a composition, and an orbit. The simulations track how they collide, how they stick together or shatter apart, and how they drift over decades and centuries. The challenge is to arrange this digital dust in just the right way, in dense, irregular clumps on eccentric, overlapping paths, so that when the virtual star's light passes through it, the computer generates a dimming pattern that matches the one we actually see from Earth. It is a puzzle with near-infinite variables. One team might program in the aftermath of a planetary collision, seeding the orbit with debris of various sizes and watching it evolve. Another might model a migrating giant planet plowing through a dense asteroid belt, its gravity shepherding dust into a trailing, clumpy wake. The supercomputers calculate the gravitational interactions and collisions for millions of simulated particles over thousands of virtual years, a process that can take weeks of real time to complete. Often, the initial results are disappointing. A model might produce a deep dip, but it is too symmetrical. It might create an irregular pattern, but the dips are not deep enough. Or it might successfully mimic the short-term blackouts but completely fail to explain the century-long fading trend. Getting all the pieces to align, the depth, the shape, the duration, and the long-term decline feels like tuning a radio with 100 different dials, where turning one knob to fix the bass completely distorts the treble. The difficulty underscores just how special and extreme the environment around Tabby's star must be. It is not just dusty, it is chaotically, improbably dusty in a configuration that our most powerful simulations struggle to naturally produce. This computational struggle is itself a vital clue. It tells us that if the answer is a natural dust swarm, then we are likely missing a key ingredient in our models. Perhaps there is a type of particle cohesion or electrical charging in space we do not fully understand. Maybe the star has a powerful magnetic field that structures the dust in strange ways. Or it could be that we are witnessing not one event but a perfect storm of several, a collision plus migration plus an active asteroid belt all happening at once. Each failed simulation narrows the possibilities, guiding theorists toward more exotic and refined ideas. These digital laboratories are where the alien megastructure hypothesis meets its most rigorous mathematical test, too. Could a model of a vast, incomplete swarm of solid collectors produce the light curve? In principle, yes, but such a model introduces even more bewildering questions about stability, construction, and purpose that have no analog in physics. The supercomputer's cold logic shows us that while an artificial structure remains a remote possibility, the path of least resistance, the one requiring the fewest new assumptions, still points toward a universe of natural, if extraordinarily violent, beauty. Every time a simulation fails to match the data, it is not a defeat. It is a step forward, eliminating a wrong turn in the maze. The flickering light from 1,000 light years away is setting the agenda for some of the most complex computations on Earth, a silent command that pushes our understanding of cosmic chaos to its very limits. The flickering light of a distant star did more than baffle scientists. It ignited the global imagination. Tabby's star leapt from the pages of academic journals to the front pages of newspapers and the trending feeds of social media. Its story framed by a single, electrifying phrase, alien megastructure. That idea, though always a long shot, acted as a cultural catalyst. Headlines did not ask about irregular dust clouds, they asked, have we found aliens? Television shows from documentaries to late-night talk shows dedicated segments to the mystery, their hosts marveling at the possibility. The star even found its way into music and fiction, becoming a shorthand for cosmic wonder and the tantalizing unknown. This was not just about astrophysics, it was about a primal human question, one we have asked since we first gazed at the campfire of the night sky. Are we alone? Space mysteries like this one tap directly into that deep well of curiosity and our innate sense of wonder. They remind us that the universe is not a static backdrop, but a living, dynamic, and often inexplicable place. In a world saturated with information, the enduring enigma of a single twinkling point of light cuts through the noise. It represents a puzzle that belongs to all of humanity, a shared what-if that requires no special degree to ponder. This collective engagement has a profound side effect, inspiration. For every person who clicked on a sensational headline, a few lingered to read about light curves and citizen science. Students who might never have considered astronomy found themselves drawn into a real-time detective story. The star became a gateway, demonstrating that science is not a settled list of facts, but a living process of questioning, collaboration, and staring into the dark until a new clue flickers into view. By making the process of mystery-solving public and participatory, Tabby's star invited everyone to become a stakeholder in discovery. It encouraged a new generation to look up, not with passive awe, but with active, questioning eyes. The ultimate legacy of this star may not be a definitive answer about dust, but the undeniable proof that our hunger for cosmic stories is itself a powerful force. one that can turn a single anomaly into a beacon for collective wonder and a renewed desire to explore. The deepest questions raised by this star reach far beyond telescopes and supercomputers. They force us to confront the profound economic and philosophical implications of a discovery that could one day rewrite our place in the cosmos. Let us play out the ultimate scenario, the one that first captured the world's imagination. Suppose, against all odds, the final evidence pointed not to dust but to intelligence. The confirmation of an alien megastructure would be the single most consequential event in human history. Our reaction would be a seismic shock, reverberating through every facet of society. There would be no blueprint, but there are protocols. Scientists and diplomats have quietly prepared for such a moment for decades under frameworks like the Declaration of Principles concerning activities following the detection of extraterrestrial intelligence. The first step would be verification, an urgent, secret collaboration among the world's observatories to confirm the signal is not a hoax or a natural mistake. Once confirmed, the United Nations would likely become the central forum for deciding how, when, and what to tell the public. The announcement itself would be a delicate global undertaking aimed at preventing panic while conveying the staggering truth. The economic and technological impact is difficult to overstate. Global priorities would shift overnight. Funding for space science and engineering would skyrocket, not as a matter of curiosity, but of species-level security and ambition. Entire new industries would emerge, focused on deep space communication, advanced materials, and energy systems inspired by the technology we were observing. The stock markets would likely swing wildly as investors tried to price in a future now utterly transformed. The philosophical and cultural upheaval would be even deeper. Every religion, every system of philosophy, every notion of human uniqueness would be examined under a new galactic light. The simple knowledge that we are not alone and that intelligence can reach such staggering technological heights would simultaneously humble and unite our species in a way no earthly conflict ever could. It would present both an unimaginable opportunity and a sobering mirror, showing us both our potential and our profound infancy. Yet the far more likely outcome, that this is a spectacular natural phenomenon, carries its own revolutionary weight. If the chaos around Tabby's star is natural, then we are learning that planetary systems can be immeasurably more violent, dusty, and dynamic than our own serene solar system ever suggested. This forces a rewrite of the standard models of planetary formation and evolution. We may be witnessing a previously hidden phase, a period of catastrophic collisional grinding that lasts for billions of years in some systems. The new physics we glean from this, how dust clumps, how debris clouds evolve and obscure light, will refine our understanding of every dusty disk we see, from newborn stars to the remnants of ancient collisions. This knowledge is the bedrock for accurately interpreting data from future telescopes, allowing us to read the history of other solar systems with greater clarity. Ultimately, this star champions the immense value of curiosity-driven science. There was no obvious practical application in studying its flickering light. No one expected it to cure a disease or build a better smartphone. Yet, the pursuit of this pure mystery mobilized a global community, advanced our observational techniques, trained a new generation of scientists and citizens, and expanded the boundaries of what we consider possible in the universe. It reminds us that the greatest returns on investment are not always measured in profit but in perspective. The relentless collective pursuit of a why for its own sake is what propels humanity forward, turning a single point of puzzling light into a beacon that illuminates the darkness of our own ignorance. So the evidence points us toward a natural, if spectacularly messy, answer. The current leading theory that ties together the most clues involves a giant, fragmented exocomet, or more likely, a vast swarm of them, on a long, looping orbit around the star. Think of it not as Halley's Comet, but as something shattered and apocalyptic, a mountain of ice and rock that has broken into countless pieces, each trailing an immense opaque tail of gas and dust. These fragments would be on a highly eccentric path, swinging incredibly close to the star before hurtling back out into the cold depths of its system. This single idea of exocomets on the edge of destruction elegantly explains several of the star's most baffling behaviors. The deep, irregular dips occur when these massive, dusty fragments and their long tails pass directly in front of the star from our point of view. Because the swarm is a collection of individual chunks all on slightly different orbits and breaking apart at different rates, their transits would be chaotic. One fragment might block a huge amount of light for a few days, while a cluster of smaller ones might create a jagged, multi-peak dimming event. The tails themselves are not solid. They are clouds of fine dust and gas, which explains why the dimming is not perfectly achromatic. It matches the fingerprint we finally saw, where blue light is scattered more than red. This model also offers a compelling, though still extraordinary, explanation for the century-long dimming. If the swarm is vast enough and on a wide enough orbit, it could create a persistent, diffuse cloud of the finest dust particles. This dust, slowly spreading out along the comet swarm's orbital path, would form a semi-permanent, uneven veil around the star. From our distant vantage point, this veil would cause a gradual, overall decline in brightness, exactly as the historical plates recorded. It is a two-part obscuration: the sharp, deep shadows of individual comet fragments and the faint, lingering haze of their collective debris. This theory is powerful because it uses a known cosmic phenomenon, comets, and simply scales it up to an almost unimaginable degree. We have observed exocomets around other stars. We know they can have large, dusty tails. The leap required is one of sheer quantity and persistence. To explain Tabby's star, we need not just a few comets, but a veritable army of them, a shattered primordial body so large that its debris field can shroud a star for 100 years. This level of cometary activity is far beyond anything in our own solar system's history, even during its most violent early days. It pushes the boundaries of what we consider a normal planetary system, suggesting we are looking at a place where the building blocks of planets never quite coalesced peacefully, or where a gravitational disturbance like a passing star or a migrating giant planet catapulted an entire reservoir of icy bodies into a suicidal orbit. So while the exocomet swarm theory is the front-runner, it still asks us to accept an environment of sustained epic chaos. It solves the mystery not with a whisper, but with a roar of colliding ice and spreading dust. It paints a picture of a system in perpetual upheaval, where the night sky would be streaked with the brilliant, doomed trails of countless falling stars, a celestial fireworks display that has lasted for generations. The flickering we see from Earth is the distant echo of that magnificent, ongoing destruction. Yet the comet swarm theory, for all its explanatory power, leaves crucial questions hanging in the cosmic air. We have a compelling suspect, but the motive and the murder weapon remain frustratingly out of reach. First, what could possibly trigger such an immense, catastrophic swarm? A single comet is one thing, but a whole army of them, large enough to dim a star for a century, implies a cataclysmic originating event. Did a giant planet like a rogue Neptune plow through a pristine belt of icy bodies, hurling them all onto star-grazing orbits? Or are we witnessing the final, slow-motion disintegration of a single, monstrous planetesimal, a failed world that is coming apart at the seams? The sheer scale of the required debris is the theory's greatest weakness, a point even its proponents openly acknowledge. Next, why is the dust so incredibly clumpy? Comet tails are typically diffuse. To create those deep, jagged dips, the dust must be concentrated into dense, irregular clouds that defy easy explanation. Are we seeing the dust trapped and shaped by powerful magnetic fields from the star? Or do the particles themselves have unusual electrical or adhesive properties, causing them to stick together in strange, floating architectures? Then there are the brightening events, those sudden flares that punctuate the dimming. A simple comet swarm does not easily account for a star spontaneously surging in brightness. Could the comets themselves be volatile enough to trigger explosive outbursts when they swing close to the star's heat? Or is there an entirely separate process at play, perhaps linked to the star's own magnetic activity, that this dusty veil has only now allowed us to notice? These are not minor details, they are gaping holes in the narrative, and every good scientist knows that a theory is only as strong as its ability to close those holes. This is the true, messy heart of the scientific process. A breakthrough rarely delivers a neat, packaged answer. More often, it simply gives you a better set of tools to ask sharper, more difficult questions. Tabby's star has graduated from a baffling anomaly to a sophisticated laboratory. Astronomers now have a working hypothesis, the catastrophic comet swarm, but that hypothesis now faces a gauntlet of targeted observations and more precise computer simulations. They will watch not just for dimming, but for specific chemical signatures in the star's light that only certain ices or dust minerals can produce. They will run models that try to trigger such a swarm from a stable system, searching for the gravitational key that unlocks this level of chaos. The star's greatest lesson may be this: the universe is under no obligation to be simple or to conform to our first best guesses. Its deepest mysteries unfold in layers, and with each layer we peel back, we are reminded of how much wonder and how much uncertainty still lies in the dark. The next chapter of this cosmic mystery will be written not just by new ideas, but by a new generation of eyes. To finally solve the riddle of Tabby's star, we need instruments capable of seeing the unseen, of dissecting that faint, flickering light with a precision that borders on the magical. The future of this investigation is already taking shape in the form of telescopes so powerful they will redefine our view of the universe. Leading this charge is the James Webb Space Telescope, an instrument that operates as a cosmic chemist. While Hubble sees primarily invisible and ultraviolet light, Webb is an infrared master designed to detect the faint heat signatures of the universe's coldest, most distant objects. For Tabby's star, this capability is revolutionary. Webb cannot just tell us if dust is present, it can tell us what that dust is made of. As starlight passes through the mysterious cloud, specific molecules and minerals within the dust will absorb unique fingerprints of infrared light. Webb's exquisite spectrographs can read those fingerprints. Is the dust rich in silicates like pulverized rock? Does it contain ices of water, methane, or carbon dioxide, pointing to a cometary origin? Or are there more exotic compounds that suggest a different, violent history? The chemical composition revealed by Webb will be the most definitive clue yet, allowing scientists to distinguish between a shattered asteroid, a swarm of icy exocomets, or something even stranger. It is the difference between knowing a shadow passed by and knowing the shadow was cast by a man, a mountain, or a machine. On the ground, a new era of giant observatories is dawning. Projects like the Extremely Large Telescope, or ELT, under construction in Chile, will gather more light than any optical telescope in history. Its primary mirror will be nearly half the length of a football field, a colossal eye that will collect starlight with breathtaking sensitivity. For Tabby's star, the ELT will not just measure dips in brightness, it could potentially map the structure of the dust cloud itself. Using a technique called advanced spectroastrometry, it might detect how the star's light is distorted as it filters through different parts of the obscuring material, revealing the cloud's shape, density, and motion in stunning detail. We could watch the clumps evolve in almost real time, tracking their orbits and watching them disperse or reform. These tools represent a fundamental shift from passive observation to active interrogation. We are moving beyond watching the flicker to understanding the flame and the hand that waves before it. Every future dimming event will be a data bonanza, a flood of spectral information that will turn vague theories into concrete models. The anticipation among astronomers is palpable. They have a suspect, a working theory of catastrophic cometary chaos, but they lack the forensic evidence to secure a conviction. Webb, the ELT, and their peers are the detectives who will finally enter the crime scene, dust for fingerprints, and analyze the debris under a microscope. The star's long silence, its patient flickering across the centuries, may soon be met with answers as clear and definitive as the questions it has asked. The final verdict on this cosmic mystery is waiting in the light, and we have just built the instruments to read it. The hunt for Tabby's star has given us more than a potential answer, it has given us a blueprint. This entire saga has quietly revolutionized the way astronomers search the sky, forging new methodologies for finding needles in the cosmic haystack. Before this star, telescopes like Kepler were designed to find the expected, the rhythmic dips of planets. Now, the goal has expanded to find the unexpected, the anomalies that break every pattern. This shift is powered by sophisticated data mining techniques and machine learning algorithms, trained not just to recognize a planet's signature, but to flag anything that looks weird. These algorithms act as tireless digital sentinels, sifting through petabytes of starlight data from missions like TESS, searching for that one erratic heartbeat among millions of steady pulses. They look for stars that dim too deeply, too irregularly, or in ways that no known physics can easily explain. It is a deliberate search for cosmic outliers, and it is already turning up more candidates that behave in strange, shadowy ways. But the real lesson goes beyond just new data. Tabby's star taught us the immense power of looking back. The discovery of its century-long fade was only possible because of long-term archival studies, the painstaking analysis of century-old glass photographic plates stored in observatory vaults. Those fragile archives transformed from historical curiosities into vital forensic tools. They proved that some cosmic mysteries unfold on timescales longer than a single human lifetime, and that the key to understanding the present often lies buried in the past. This creates a thrilling possibility for any aspiring discoverer. The next great space mystery might not require a new telescope pointed at the sky. It might be hiding in plain sight, waiting within the mountains of data we have already collected. Imagine a curious student, a retired engineer, or a programmer downloading publicly available datasets from a space telescope archive. With the right algorithm, or even just a keen, patient eye, they could scan the light of a million stars and spot the one that flickers wrong. The tools for discovery are increasingly democratic. The next anomaly could be found by anyone, anywhere, who asks a simple question of the data: what does not belong? The universe is vast and strange, and we have only just begun to look at it with eyes trained to welcome the inexplicable. This beautiful frustration is the very heart of discovery. When a star like this one leaves scientists completely stumped, it is not a sign that science has failed. It is a sign that science is working exactly as it should. The entire journey we have traced, from that first citizen scientist's click to the supercomputer simulations, is a perfect case study in how human curiosity evolves when confronted with the unknown. True progress is not a straight line from question to answer. It is a messy, collaborative stumble through the dark, where every wrong turn and every dead end illuminates a new path forward. Tabby's star did not give us easy answers, but it gave us something far more valuable: better questions. It forced astronomers to challenge their most comfortable assumptions about how planetary systems form and behave. It compelled them to build new tools for global observation and to write new algorithms for finding the strange. It turned a solitary anomaly into a shared project for thousands of people across the planet. This is how knowledge grows. We build a model of how the universe works, a kind of cosmic map, and then we encounter a star that is not on the map. That moment of confusion, that thrilling state of being stumped, is the signal that our map is incomplete. It is the catalyst that drives us to explore the blank spaces, to redraw the lines with finer detail. Every great leap in understanding begins with a stubborn fact that refuses to fit. The flickering of this distant star, in all its infuriating mystery, has already expanded our vision. It has taught us to look for chaos, to value collaboration over solitary genius, and to embrace the profound truth that the universe will always be stranger and more wonderful than our best theories. The star's final gift may be this reminder: the destination is not nearly as important as the journey of collective wonder it inspires. That flickering light in Cygnus has rewritten the rules of cosmic curiosity. We began with a single, jagged line on a graph, a scream of wrongness in the silent data of the Kepler telescope. It launched us on a journey from the thrilling specter of alien megastructures to the chaotic reality of catastrophic comet swarms. We watched as citizen scientists made the first discovery, as professional astronomers mobilized a global stakeout, and as supercomputers struggled to simulate a level of chaos that defied easy explanation. The alien hypothesis, while a captivating cultural lightning rod, has faded against the hard evidence of scattered blue light, pointing us firmly toward a natural, if spectacularly violent, answer. Yet declaring the case closed would be a profound mistake. The true legacy of this star is not the solution, but the scale of the mystery it revealed. We have traded a simple question for a universe of deeper, richer complexity. The idea that we might be witnessing a system in the throes of epic, sustained destruction, a place where worlds shatter and skies fill with the dust of 100 falling stars, is arguably more wondrous than any silent alien artifact. It proves that nature's imagination far exceeds our own. This star did more than baffle scientists. It trained us all to look at the night sky with new eyes. It taught us to value the anomaly, to embrace the collaborative hunt, and to find profound excitement in the simple, humbling admission that we do not yet have all the answers. So the next time you find yourself under a clear, dark sky, take a moment to look up. Somewhere in that vast ocean of light, another strange star is almost certainly flickering its own coded message, a puzzle waiting for the right curious mind to notice. The universe is not a solved equation, it is an endless story, and we have only just begun to read the first few breathtaking pages. The story of this star is yours as much as it is science's. So what do you think is really happening out there? Is it a cosmic demolition derby of colliding comets, a young star's violent tantrum, or something even stranger that we have not yet dreamed of? Drop your own theory in the comments below. This mystery belongs to everyone who looks up and wonders. If you want to join the hunt for the next great space enigma, make sure to subscribe and tap that notification bell. Our universe is filled with unexplained flickers and cosmic riddles waiting to be solved, and you will not want to miss what we uncover next. As the screen fades, watch that single point of light, 1,400 years away, dim and brighten in its silent, unknowable rhythm, a reminder that the greatest stories are still written in the stars.